Okay, so our next speaker going to be Samy, and he's going to speak on simplicity perform, but should it unity malware detection benchmark. Samy, it's over to you.
Um, Hello everyone, I'm Samy from Ouytsel in Belgium, and this is joint work with Laurence from Ghent University in Belgium, and is also here in the audience today, and Charles-Henri from Ouytsel. Our work is an evaluation and analysis of malware detection benchmark datasets. So let's start with some context. So maybe some of you are familiar with these kinds of graphs showing that the amount of malware and potentially economic applications keep growing through the years. And this growth emphasizes the need for efficient, effective, robust detection methods that can handle large amount of data and that can, as much as possible, detect new variants. Traditionally, we relied on signature-based approaches. With signature-based approaches, you have a predefined list of signatures and generally malicious signatures, and once you have a new sample, you compute its signature. The simplest example is the hash of the file. You try to see if this signature is in your predefined list. If yes, it's a malicious sample, otherwise it's a benign sample. As you might have guessed, this approach generally works well to detect known threats, but it fails to detect new ones. And unfortunately, it's very easy to modify the signature of the file with minimal changes. Also, this approach does not scale very well, because how can you handle all the possible signatures of all the possible files? This pushed the community towards machine learning approaches, where the idea is to predict what might emerge based on what we've seen, and since we have a lot of data, we might as well learn from it. Naturally, the community also evolved towards deep learning. So we've seen graph neural networks after representing the binaries as graphs. We've seen CNNs after representing them as images, and a bunch of NLP-inspired methods. And of course, in the last 2 or 3 years, we've seen LLM-based approaches. Basically, a trend in increasing complexity and computational cost. But you have a few problems with that. First, usually reproducibility is lacking, because lots of data sets are not available. So you have lots of papers that say, here's our new model, we achieve 99% accuracy, but we can't share our data sets, so you have to trust us with that. And that's the problem. I think we should acknowledge that sometimes it's very hard to share the data, because your cleaner provider or your antivirus provider does not want you to share the samples. So that's a difficult problem to solve. And I don't think that this work does not have any kind of value, but I think we all agree that it's better to be able to reproduce the results. Also, there's the lack of comparison with simple baselines. So we don't know if these high accuracies we see are related to the model itself or to other factors. And that's my next point, because we see high accuracies everywhere, yet the malware problem is still here. And that means that something does not add up. What if instead of building real malware detectors, we're simply building academic benchmark solvers? Of course, academic datasets do not reflect the real world diversity. This leads us to our research questions. First, we ask ourselves, how do simple models perform on public malware datasets? And we also ask ourselves, do we have certain features that dominate the classification in a non-intended way? To answer these questions, we will compare 4 models with increasing complexity on 11 public datasets. We will show evidence that complex models are over-evaluated when using these datasets. We will insist on the value and importance of using simple baselines. And we will provide concrete examples of dominant and discriminative features that influence the decision of the models in a non-intended way. With that, we also provide an in-depth analysis of the Amber features. The Amber features are a set of 2,381 features that are referred to as state-of-the-art in Windows malware detection with machine learning. With all of that, we also provided clean, usable datasets and code, and they're all available on Kaggle publicly. Now let's move on to our models. So we use two simple models. The first one is a one-node model. It's basically a decision tree with one node that learns using one feature. And then we have the AdaBoost model, which is a sequence of big learners. And on the complex side, we have LightGBM, which is an efficient gradient boosted decision tree, and is often referred to as the state-of-the-art in malware detection using tabular features, in particular the AMBER features. We also have the FastAI tabular learner, which is a small neural network for tabular data. We have to say that LightGBM and FastAI tabular learner, they're still simple models compared to an LLM-based approach or reinforcement learning approach. But compared to the one-node model, they're still quite an upgrade. And that's why in this context, we separated them as simple models and complex ones. And the idea is to see if we can go far with the simple models, or we really do need the complexity of the complex ones. Now let's move on to the data sets. So we use 11 public data sets. Most of them are Windows datasets, so from the AMBER interdimension FC, and we also have Android and malicious PDFs datasets. To avoid confusion, we have the AMBER datasets and the AMBER features, and they're not the same thing. Basically, when the AMBER paper came out, it introduced datasets and a feature extractor that extracted a set of features that became known as the AMBER features, and that's referred to as state-of-the-art. And that's why all of the Windows datasets use the AMBER features. Only the backward dataset uses the AMBER features along with a bunch of other features. All of these datasets have their own malicious internet samples. Only Motif and BenchNFC are malicious-only datasets, and that's why we added to them a bunch of demand samples that we collected on our own from the Chocolat Team Windows Package Manager. For evaluation, we started by cleaning the datasets. We handled missing values, removed duplicates and metadata. You should always remove the metadata from the datasets, and lots of papers and works do not do that. We also did a few optimization on the data types. And then we evaluated the different models on the different datasets and recorded metrics such as the OROC, F1 score, precision, and recall. And after that, we performed the feature analysis to identify or understand the features that influence decision. I will provide a few examples of these features, but if you want an in-depth discussion, don't hesitate to look at the paper. So this is our first results. Don't worry, it's the only massive plot in this presentation. I recorded the OROC here, but if you want the other metrics, I can still show them later. Basically, it shows the performance of each of the 4 models on each of the 11 datasets. The first thing that we see is that LightGBM, which is regarded as the state-of-the-art, as expected, performs great on all of the datasets. The other thing that we see, which was not very expected, is that AdaBoost is not that far from LightGBM actually on most of the datasets. The other interesting results is that the one-node model is not that bad either on all of the datasets. The next comment that I make is that on the x-axis, datasets are sorted by size. So the AMBER 2017 is the largest dataset, and the Motif is the smallest one. And we see that for the very large datasets, we start to observe the most natural or expected tendency between the models, with the one-node model as the worst one, then the AdaBoost, then LightGBM, and the neural network somewhere in between. We will try to analyze these features, these decisions, by analyzing the features. These are the distributions for the 3 best features on AMBER 2017. These are the most discriminative features. We have DLL hesitators, the presence of relocation entries, and the presence of debug info. Due to the time, I'll directly speak about the debug info, but maybe we can have a better discussion afterwards about the rest. For the debug info, what we see is that the samples, while most of the malware do not. You might say it's normal because the malware is heavily obfuscated, packed, and do not want to be reverse engineered. You're right, but there exists a bunch of benign samples that are also obfuscated, packed, and do not want to be reverse engineered. It's just that in the Ember 2017 dataset, they are not present. And that's why if you train your model on Ember 2017, and then you try to test it on another dataset, or in the real world, it does not work and your model breaks. If you look at the feature distributions of the 3 best one-room models, or BODMAS, we also observe a few discriminating features. We have first the number of URL strings, the certificate table virtual size, and the timestamps. If you look at the timestamps, what we see is that the benign samples are better distributed over time, while the malicious samples are clustered around here, and I think they span over a 1-year period. That's a problem, because the timestamp alone should not be a discriminative feature. Some of you might argue that we should remove the timestamp with the metadata because it does not reflect any malicious behavior. Others might argue that the timestamp in correlation with other features might give you insights into some suspicious behavior. That's open to discussion. I'll let you discuss it. But in either cases, I think we should all agree that we should have a better distribution or equivalent distribution in both classes in a perfect world. Because otherwise, these features do not reflect malicious behavior, they merely reflect some dataset collection queries or dataset attributes. If we look at the certificate table size, you might say, okay, it's natural that most of the benign samples are certified or signed, while most of the malicious samples are not. And I think, yes, it's true, but nothing prevents the malware author to sign or certify his sample. And actually, that's what we see here. Some authors tried that. Unfortunately for them, they did not fall into the benign sample distribution, but theoretically, nothing prevents that from happening. Now let's go back to our research questions. The first one is, how do simple models perform on these academic public malware datasets? And the second one is, do we have certain features that dominate classification? For the first one, simplicity performs. It's clear that it works well, but is it enough? Does it mean that we should always use the one-room model and discard all of the complex work that we have? No, that's not our message. That's not what we're trying to say. What we want to say is that the data sets are too easy to solve regardless of the model that you use. So maybe the 99% accuracy that you have is not related to your new fancy LLM, but it's just your experimental setting that is too easy. So academic benchmarks can be misleading, and that's why we should always have a simple baseline. So, because without them, we can't say for sure if the complex models are as good as we think they are. For the second question, yes, we have clearly a few features that are discriminative. That's why we should always think about what our features are expressing, for the features that are, and the features that are actually used in the decision. You should always also think about the variability of the dataset and the distribution between the classes. We didn't speak too much of that here, but you also shouldn't use only accuracy to evaluate your models. Don't forget generalization by using out-of-distribution datasets, hidden datasets, and of course robustness to adversarial attacks. Here it didn't make much sense to evaluate robustness because a model that is using only one feature is clearly easily attackable if we change that feature. Now to conclude, on the big scheme of things, I think we need more research into dataset quality. We also need more research into expressive feature representations and semantics. Because, for example, if you use images, what does the image express about the malware? What does it mean? same thing with graphs and behavior graphs. What is the definition of a malicious behavior? It's still an open question and a difficult one. Our contributions consist in the evaluation of simple and slightly more complex models on these academic public datasets. We also provided an analysis and mapping for the Ember features, and we released our clean datasets encode, and they're all available on Kaggle. And to conclude, I'd like to say that we need stronger and more realistic evaluations, not only complex and fancy detection algorithms. And with that, I thank you for your attention and be happy to answer your questions. Thank you.
Let's move to questions.
Thank you for the talk. So what's the assumption here about the training that these models that you benchmark go through? Do they train on the same data set or different data set? Do they train at the same time at different times? Because distribution drift or data drift may affect these results of these models. So unless you have you normalize the training and everything at the same time, the same data sets, and then you test on the same data sets, you cannot come to these conclusions, right?
So you repeat the question, make sure I understood it. So you're asking how did I train the datasets or the models on the datasets?
So do you have these models trained on the same datasets?
Okay, so we evaluated the models on the datasets, but each dataset is independent.
Yeah, but the models, did you train the models or did you use trained models?
We trained the models ourselves. So we trained the models on each dataset alone. It's an independent experiment. So we trained each one model on each of these datasets here and evaluated independently. I don't know if it's answered the question. We also made an experiment where we merged all the datasets together, but the results were kind of the same tendency as we observed on the others. Maybe I did not understand the question.
They use different features, or the features that they use, they not
They
exist
use
on
the
the
same
data
features
sets that they have. I mean, as if you are comparing apples to oranges, this.
So I think what you are saying, you create a different model for each data set.
Yes. And all of the features that are used are here. So the Windows datasets use all the Ember features. So it's the same 2,381 features, only the backward dataset, because in the literature it came with more features, and that's what we used. So here I didn't want to overload the slide, but all the datasets here have the appropriate citations in the paper. We used public ones, public datasets. We have their own public set of features. And the Windows use all Ember features, and the others have their own custom features that are all described in the paper.
So you train and test on the same data set, or you train on a data set and test on the remaining ones?
No, what he's saying, he trained the model for each data set and test the same model with the same data set.
Yes, so
second data set.
we take the Ember dataset. The Ember dataset has predefined split between test and train. We use the train set, we evaluate it on the test set. Then we take BODMAS, we split it into training and testing. We train it on the train, and we evaluate it on the test set from BODMAS.
Did you try generalizability as a measure? For example, if you train on one data set and test on the other?
We did not do the experiment because it was not the result that we want to show. Because it's obvious, for example, the IDS dataset, it's a dataset with obfuscated malware, obfuscated files. It's to detect obfuscation. And we've seen that the debug info is a discriminative feature on the Ember dataset already. So it was clear that if we change the dataset, it should have broken the model. But it's not. Our goal was not to compare the models to find the best model or the best dataset. Our goal was to show that these datasets alone are too easy and they cannot be used as a lone benchmarking metric.
Excusez-moi, 1 minute. Le code de la porte. Écrivez le code de la porte, s'il vous plaît, parce que personne n'a le code. Écrivez le code. 4823A.
Sorry, someone can translate it with English, please?
4823.
I think it's about the code on the door outside.
A, the letter A. The last one is the letter A.
Ah, lettre A. 48 23
Hey.
A. 48 23 A.
Thank you. Question?
Yeah. Thank you, Samy, for the talk. Perhaps related to that, I'm just curious with regard to the proportion of the benign and malicious number of samples. Are they balanced? Are they, what are the, I probably missed this somewhere, but I don't know what proportions are the benign and
It's the distribution is in the paper. It's not described in the slides, but it depends on the data set. So there are ones that are not balanced and ones that are more balanced than the others.
okay, so now there's a bit of differences. Some are balanced, some not balanced.
Yes.
How you make sure that you can still get some sort of
Sorry?
how you can make sure that even though it's not balanced, you can still get similar in cycle. What do you come up with this imbalance? How do you deal with imbalance in this?
We did not try to fix the imbalance because these data sets, when they're used, they're usually used as a whole. So we use them as they are usually used. And then if we were, the other solution would have been to like downsize the data sets, and which is not also a great approach because then you can say, why did you remove this sample and not another? So I agree that it's not perfect settings, but the solution wouldn't have been better, I think.
Okay. Yeah, I was just wondering about
Yes,
the risk of
I
bias
agree.
in there because now in some data set might have a bit more risk of getting it, benign all the time because it's not
Yes,
wrong.
yeah.
Anyway,
I agree.
exactly. Thank you.
Thank you.
Just a quick question from me because the Bertrand, I noticed you were split between training to test is 20 to 80.
Yes,
Is that correct?
yes.
So your training set is 20% and
Yes.
test set is 80%. Is there a particular reason you wanted to? Because I have some other concern because if you split, if your training set is very small and the test set is huge, then sometimes the distribution bias can happen. Also data leakage can happen, and then that can goes to higher accuracies. Is there a particular reason why you wanted to use that unusual split?
Well, first, the training is faster like that, and also it has been shown that for lots of data sets, the training size, sometimes we don't have to go to the classic 80-20, because sometimes it works well with 80%, and that's the case here because if we see all of our data sets have different sizes. So like increasing the training size did not really that much affect the performance of the models. We used 2080 if the predefined split was not already defined. For the Amber datasets, there was already predefined split, and that's what we used.
Yeah, but the problem when the training set is too small and the test set is too large, then the data leakage can happen. And I'm not sure that you consider, and also distribution bias can also happen because some similar training kind of samples can be existed in the test set when the training is too
It's
small.
around the minus 20% split.
If you try the other way around and also observe the similar accuracies, I think it should be fine.
We tried the other way around and we saw the same tendency. That's why we kept it 20%. But actually, yeah, like I said, you see the data sets have all different sizes, and we observed the same tendencies with all the data sets. So that's why we did not keep it like that.
Thank you. Let's thank the speaker. So this brings our first session to the conclusion before the tea break. and we're going to start our next session sharp 3:35. Okay, so please come back on time because we need to finish today to go to the board